In this last hands-on lecture, we are going to implement a multivariate weather forecast with the LSTM model. Well, actually, we will just forecast temperatures, but you could easily extend this to a full weather forecast. However, what does multivariate mean in this context? It means that we will have several input variables per time step. We also used to call them features. In this example, we will use several features like temperature, relative humidity, precipitation, and global radiation as input features to predict a single output feature, which is the temperature of the next day. You might remember the RNN types we discussed in the previous lecture. This will be a many-to-one translation. As the training data preparation will be a bit different this time, we should briefly discuss it. We have a data sequence of length n, which will be our x data and includes all input features. A single value of the temperature for the time step n plus 1 will be our y data. So the first record in our training data will roughly look like this illustration, with a block of features over several time steps for the x data and the temperature of the next day as the corresponding y feature. So we provide the temperature of the next day so the model learns how to make a forecast. For the second record in the training data, we shift our window for the selection by one step. And repeat this for the third one, etc., etc. I think you get the concept, so let us start to implement this. As the last times, I have already added those imports that we have discussed in previous videos and will add those that are new. We will use a different method for normalization, respectively standardization this time, which comes from sklearn.preprocessing and is the standard scaler. Then we also need all the different layers for our model, which we import from TensorFlow.keras.layers, and we will need LSTM, dense, and dropout. Now we can start with the data preparation and import our weather dataset. We again use pd.readcsv for that and specify the file path, which lies relative to this script in the subfolder data and is called rgsdata.csv. Let me just print it so we see its content. Scrolling through the dataset, we notice two things. First, we have a date column which has a format that we cannot push through a network. And second, there are columns that obviously hold NaN values. Let us take care of the date format first. To investigate the data frame's current data types, I just call dtypes on our df. The date column holds Python objects and is thus the only column that holds an unsuitable data type for a deep learning model. Nevertheless, the date might hold relevant information for the LSTM cell to predict the temperature of the next day. For example, it is unlikely that the next day's temperature is 25 degrees Celsius when it's December in Germany. Well, at least not yet. To preserve some information about the date while having a suitable format for it, I will turn the date into a day of year format. To do that, I grab the date column and turn it into a datetime format with ed.datetime and provide the date column as an input. Based on that, I can now calculate the days of the year, which I will write into a new column called DOI. Then I take the date column and say .dt .day of year. Taking a look at the dataset now, we find the new column at the very end. And as the first entry in this dataset is from the 1st of January 2019, it has the DOI 1. The last day in this dataset is from the 22nd of November, so it has the DOI 326. Now we somehow should get rid of those NaN values, and I'm going to pursue an avoidance strategy this time. We have so many input features in this dataset, and the NaN values only seem to be present in a few columns that I will just pick those columns that do not have any NaN values. Having too many input features might even cause computing problems on some machines, therefore a reduction does not seem to be such a bad idea. As calling each column that I want to keep by its name seems to be a lot of desk work, I will just provide their indices. And to have a better overview over the indices, I will create a pandas series that holds the column names of our dataset. Now I can see the column names and their index, making it simple to select the columns with the ilog method. So I set up a new variable that will hold the training data frame, then get our df with the ilog method, select all rows, and provide the indices within a list. And I want to keep indices 1, 2, 6, 9, 15, 16, 18, 19, and 39. Then I should check that there are really no NaN values left in those columns. So I say isNull dot sum on our data frame. And here we see the selected columns, like temperature, relative humidity, wind speed, or air pressure, and none of those have any NaN values. Next, we should take a look at the data frame's statistics. So training df dot describe. You see that the value ranges and magnitudes vary a lot between the different features, like a wind speed between 0.4 and 5.9, and an air pressure between 963 and 1030. So we definitely have to fix this issue, and I will do that with the standard scaler, which standardizes the features to a mean of 0 and a standard deviation of 1. First, we need to set up an instance of the standard scaler. Then fit it to our data, and apply the transformation on our training data frame. I will store the transformed results in a new variable. Then I check the statistics again, but need to turn it into a pandas data frame first, as the standard scaler turned it into a NumPy array. Now all feature values lie somehow around 0, and they no longer vary so much from one another. Thus we can set up our x and y data. The way I will set this up might seem overcomplicated, but it should just make the script less hard-coded, so we can easily change parameters for playing around and test a different length of time steps. First, I need an empty list for xtrain and ytrain. Then I need a variable that holds the number of days we want to predict into the future. And as we currently just want to predict the next day, I set it to 1. Now a variable for the number of past days that will be used to predict the future temperature, which I set to the past 7 days. The generation of the data sequence for X data and the corresponding Y data will now happen in a loop. Let me first write down the full expression for that. For I in range, n past, comma, len of scaled train df minus n future plus 1, comma, n future. So what does that mean? The counting should start from the variable n past, which we set to 7. Why 7? Because I will grab the X data sequence backwards from the counter and select the first 7 days for the first sequence. Then the middle part between those commas, which is the maximum count that should be reached. The maximum that could be reached is the last record in our dataset, which I grab with the length of the data frame. Then I remove the future steps from that because from the counter onwards, I want to select the Y data. And if I move too far, I would overshoot the last record. Then I add 1 because during slicing, the second value is exclusive. You might ask yourself, why do I subtract one future step and then add 1 again? This does not seem to make much sense. And you are absolutely right about that. I just did that so the code is flexible, and we can also set up more future steps than just 1. Let me just print the value of I, so things get clear. You see that the first value is a 7. If I count backwards from there, I can select the past days. Then the value rises by 1 in each step until we reach 1421, which is the last index in our data frame. If I change the number of future steps to 2, the counter will also start at 7, but now adds 2 in every step it takes until it reaches 1419. Even if we then search for the temperature of the 2 future time steps, we will not overshoot the last entry in our dataset. But let us change the number of future steps back to only 1. Now we need to figure out the right selection method for our X data. We always need a pair of indices, one for the first data point in the sequence and the second as the end point. So for the X data, our first index will be I minus n past, and the second, the I itself. This way, the first selection would use the indices 0 to 7, where the 0 is inclusive and the 7 is exclusive. So we only have to put this expression into a selection and add the result to our X train list. Now we need to select the corresponding future temperature that we want to predict. I will again write this in a way we could theoretically extend the number of future steps. The Y data should be selected from the current I up to, but not including I plus n future. Let me add some dashes between the printed information so we can see which indices belong together. So the X data for the first entry in our X train data will hold the data from index 0 to 7, not including the 7 itself. And the Y will be taken from index 7 up to, but not including index 8. So basically just index 7. So the indices seem to be correct, and we can also implement the selection for the Y data. Here we also need to take care of the columns that we select. Currently, all columns would be selected, but we only want to predict the temperature. The temperature data lies in the column with index 0, so I just select this column here. That's it. We created our X and Y data, but they currently have the data type list, so we quickly convert them into NumPy arrays. You see that we have currently 1415 training sequences, where each of the X data has got 7 time steps of 9 features each. And the Y data is just 1515 times the corresponding temperature of the next day. Now we can finally set up our LSTM model. As always, I set up a sequential model. And add the LSTM layer to it. I will only use a single unit, so a single LSTM cell, like we have seen it in the theory lecture. For the input shape, I need to provide the number of time steps and the number of features per time step, which I grab from the X-train shape at index 1 and index 2. That's the model for now, so just a single LSTM cell. Then I need an optimizer, for which I will use keras.optimizers.addem with a learning rate of 0.002. After that, we compile the model, provide our optimizer, and define a loss function, for which I will use MSE, so the mean squared error. Then I want the summary to be printed and fit the model to our data while saving its progress in a history variable. I provide X-train and Y-train, set the number of epochs to 30, the batch size to 16, and this time I also specify a validation split, which I set to 0.1. You might have noticed that I have not generated a test dataset this time. We can also separate data for testing within the fit function. As I have not specified a random shuffle, Keras will separate the last 10% of the data for testing and will provide a validation loss during training. Now I execute that cell and see that the training and validation loss slowly decreases. I will just copy some code to plot the training and validation loss in a graph. As you can see, I can access the training and validation loss within the history dictionary to separately plot them. Let us push the whole dataset through the model to predict the whole time series. As we trained the model on standardized data, it also makes its prediction in that value range. So we have to invert the standardization in order to get the predictions in degrees Celsius. Before we do that, I want to add 2 more lines of code, which currently do not make a lot of sense, but will do later on. First, I flatten the forecast array, so all values are written behind each other. Then I use np.expanddims to add the dimension we have just removed back to the forecast array. Currently, this seems to be nonsense, but I will come back to that. Now back to the problem with the standard scalar. The scalar that we set up for the standardization indeed has got a function inverse transform, which can undo the transformation, but there is a small problem. We fitted the scalar to our 9 input features, thus it expects the input to have a shape of 9 features. Now we only have a single feature that we predicted, which does not fit the shape of the scalar. We will use a small trick to make the scalar believe our prediction has got the correct shape. For that, we will just repeat our single prediction column 9 times, so it fits the shape of the scalar. To do that, I will use np.repeat. Provide our forecast array, define the number of repetitions, which we can just grab from the scaled training data frame's shape at index 1, and define an axis along which the repetition should happen, which is axis 1 in our case. If I print the shape now, our array has got 9 features instead of only 1, which is actually just our prediction repeated 9 times. As we have the right shape now, we can invert the standard scalar within a variable that I call ypred. Then I get the scalar from further above, say inverse transform, and provide our adjusted prediction array. The remaining problem is that the scalar used the individual mean and standard deviation for each column. So the precipitation column got standardized with different values than the temperature. That means that only the column that used the scalar for the temperature holds the correctly inverted transforms. If I scrolled up, I could see that the temperature data is in the first column. So I select all rows and only the first column, which I do with the column 1 instead of indexing by 0 to keep the extra dimension. If I take a look at the predictions now, they seem to provide the temperatures in degrees Celsius. To take a look how close the predictions are to the real temperatures, I want to create a data frame with both values side by side. I extract the dates and real temperatures first and save them in a variable real. I access our initial data frame, df, and extract the columns with the date and the temperatures, providing a list of their column names. Then we have to keep in mind that we do not have any predictions for the first 7 days, as we needed the first 7 days of data to make our first prediction. So I select all rows from and past onwards. To avoid a manipulation of the original data frame, I make a copy and then reset the index. This already looks fine. Now I turn our predictions into a data frame. Provide our ypred, give it the column name predicted, and also reset the index, just to be sure. Both real and predicted temperatures should start on the same day now. That means we can just concatenate the two data frames with pd.concat. Provide the two data frames as a list, and define the axis, which should be 1. Then I want the date column to function as the index. And now we have the real and the predicted temperatures side by side. In general, I have the impression that the predictions are not very good yet, but let us investigate that a bit further. I quickly copy some code to plot the whole data sequence. While the model seems to get the general seasonal temperature trend, it smooths out extremes and fails to accurately predict peaks. However, we must keep in mind that we mostly plotted the predictions of the training data, meaning the model got to know the data already, which arises the question how the graph looks like for unseen data. You remember that we saved 10% of the data for validation. As we have not shuffled the data, carers should have spared the last 10% of the data for testing. So let us quickly get those last 10% and see how the graph looks like for that. I mean, it is already included in the current graph, but it is too small to get any insights. First, we need to calculate the number of features, which represent 10% of the whole dataset, which can be done by this simple calculation. Then I select the validation data based on that number of validation records, counting backwards in the dataset. And then I add one more line, which is actually just for the case that we choose a different number of future steps, or we have a case in which the iterative construction of the x and y data left a remainder for which no further complete observation period could be formed. So I drop NaN rows just in case. As this is our validation time period, we should also calculate the mean absolute error to get an idea about the model's performance. and I receive a mean absolute error of over 2 degrees Celsius. I again copy some code to plot the validation data. And we see that the model really smooths out especially the first half of our observations. So can we improve the model somehow to better adapt to temperature fluctuations? Let us scroll up to our current model. First, we could not only use a single LSTM unit, but several, just like we use several neurons in a dense layer. I will use 32 for this LSTM layer. Then we could also add a second LSTM layer after that, with let's say 64 units. Now we run into a little problem. If I run the model like this, I receive an error. The problem is that the LSTM expects a sequence of data, but the first LSTM layer only returns a single value. To prevent this error, we can set the return sequences parameter to true. Now the output of each time step is returned by that layer, which can then be used by the next layer to get even deeper insights to what the first layer has already discovered. Now it is important that the last LSTM layer does not return the full sequence in our case. Then I add a dropout to prevent overfitting a little bit. And my last layer will be a dense layer, with the output shape of y trains shape at index 1. So why do I do this? Previously, the output of the LSTM was also enough. So why do I need a dense layer now? Well, using a dense layer is one option to give the model the capability to predict several steps into the future, and not just one. The number of outputs now depends on the number of future steps in our y-train data. So if we change our training data to contain the next 2 days of temperatures, the model will adopt to this. I will also reduce the number of epochs to speed things up a bit. Now take a look at the model's current validation loss, and then run this cell and all below. You see that this model reaches a lower loss after fewer epochs. Scrolling down to the graphs that we generated, we see that the predictions are way closer to the real temperatures now. The mean absolute error is now way below 2 degrees Celsius, and the first half of our validation data is not smoothed out anymore. Now let me show you one last thing. I talked about making the code less hard-coded several times. And because we kept the code a bit more flexible, we can now easily change the script to create a model that is capable to predict several days into the future. All we need to do is to change the number of future steps to, let's say, 2, and run all the cells below again. This time, the y-train data carries 2 days of temperature data, and the model's dense layer also returns 2 values. And this is what we wrote that flattened part for. Before that, we had 707 predictions of 2 consecutive days. Those got flattened to write those predictions behind each other, resulting in 1414 single data points. Now the mean absolute error got a bit worse again, which is not surprising as it is more difficult to predict the temperature for the next 2 days than just for tomorrow. Depending on the use case, this way to predict several time steps into the future might not be the optimal choice, as I predict 2 time steps in one shot. A different approach would be that I only predict the next day and then take that prediction as an input to predict the day after tomorrow. However, you see that we not only would have to predict the temperature in this case, but also the other features, as they would be missing as an input. Even though LSTMs do not suffer from vanishing and exploding gradients as much as simple RNNs do, they are not completely immune to it. They can also struggle to find relationships in very long data sequences. In recent years, LSTMs have been outperformed by transformer-based models. But transformers are beyond the scope of this seminar. So don't get me wrong, LSTMs can do a good job, but there is still a lot to learn in the world of deep learning.